Yeah, good morning. So in the last class, we have discussed about the different standard factors which were contributing to the magnitude and as well as the slope or contribution and phase angle contribution. So we'll discuss today in a consolidated way. So first factor which we have discussed is system gain K, right? First factor which we discussed is system gain K. So with this, we have found out what is the magnitude. Here, this system gain K will not contribute to the slope. We have calculated the magnitude of this 20 log K. 20 log K. This is the magnitude. So magnitude is equal to 20 log K. Phase angle contribution is 0 degrees. And now P number of poles. P number of poles at origin. Poles at origin. This is the second factor. So if you look at this, the magnitude we are not calculating here. It forms a line of a line equation, so that is why we are using the slope contribution. Slope contribution is minus 20 into P dB per decade. This is the slope contribution by the P number of poles at origin. Then phase angle, it is going to be minus 90 degrees into P. Next, third one, Z number of zeros at origin. Z number of zeros at origin. So what is the slope contribution for this Z number of zeros? That is minus 20 plus 20. For the zeros, it is plus 20 into Z dB per decade. And similarly, it is contribution is plus 90 degrees into number of zeros at origin. Likewise, the third factor is also we have discussed, that is simple pole. Any simple pole which contributes to the line of slope of minus 20 dB per decade, and corner frequency is omega c is equal to 1 by t. So omega c is equal to 1 by t, and this one is minus tan inverse of imaginary by real. So whatever it is, so we'll be getting in terms of, that is the minus tan inverse omega into t we have taken, but here I straight away write minus tan inverse of imaginary by real. And fifth one is simple zero. Simple zero contribution is going to be plus 20 dB per decade, and corner frequency is equal to 1 by t. And the phase angle is plus tan inverse of imaginary by real. Imaginary part divided by real part for complex variable, which you have considered simple pole as a simple pole. So next is one more factor. Of course, in the discussion, we have taken 2 and 3 is one factor, and 4 and 5 is one factor. Similarly, 6 and 7 is one factor. Okay. So now quadratic pole. Quadratic pole is having the contribution of plus 40 dB per decade, and omega c is equal to omega n. Corner frequency for simple pole and simple zero and quadratic pole will be getting the corner frequencies, and this one, sorry, quadratic pole, it is minus 40 dB. And also we are going to get minus tan inverse of imaginary by real. Imaginary by real. Whatever the imaginary part you have, that is the same equation will be getting minus tan inverse of. Similarly, we'll be getting for quadratic 0. Quadratic 0. These are the different factors which we have discussed in the previous classes. For quadratic 0, the slope of line contributes minus 40 d plus 40 dp per decade, and omega c is equal to omega n plus tan inverse of imaginary by array. So whatever, see the factors which I have discussed till now, these are the things which you need to know for each factor. For each factor, what is its magnitude or slope contribution? So magnitude contribution only will get in this case only magnitude k. A system gain k is contribution is magnitude, and the phase angle 0 contribution, and p number of poles if there are origin. P number of poles means if there are 2 poles or 3 poles, depends on the problem. So we may get p number of poles at origin, then we can get the slope contribution is minus 20 into p. The slope contribution is minus 20 into p. Similarly, phase angle is, there are two things which you are calculating here for every factor, right? One is the magnitude, the other one is the phase angle. So magnitude, some of the factors will be because it forms magnitude when I'm calculating for the different factors other than k, it forms the line equation. It forms the line equation. So line I cannot represent. So but I take the slope of that line and then add the algebraic, I mean slopes of all the factors which are present in the magnitude plot. Algebraically, we are going to add the slopes. So minus 20, minus 40 or plus 40, whatever, depending on the factor, we are going to add the slopes of these lines and then we'll plot the magnitude plot. We'll plot the magnitude plot, resultant magnitude plot. And actually initial Bode plot starts with the two factors. One is system gain k and the other factor is poles are zeros at origin. So either of these may present. So by combining this resultant, that was discussed in the previous classes, that is how this resultant, I mean initial Bode plot is going to be obtained. So initial slope of the Bode plot is always depends on the number of poles or zeros at origin. Number of poles or zeros at origin. So initial the slope of the Bode plot is depends always the number of poles or zeros at origin. So based on that, we start the combining of k and poles or zeros at origin. Then we'll start with the doing the from third step. I mean next step onwards. That is, we'll discuss how it can be drawn. So first, understand the factors and their contributions to the magnitude plot and their contribution to the phase angle plot. So phase angle plot, it is easy, just tabulate the values, and magnitude we need to find out the corner frequencies for the simple pole and simple zero, and then we need to go on calculating the quadratic pole and quadratic zero. Right. So next we'll move on to the how to sketch. I mean the process or procedure steps to draw. Steps to draw Bode plot. So first step is, okay, one, express the given open loop transfer function, that is g of s into h of s, in the time constant form. This is very important. Time constant That is 1 plus TS form. If it is not there, so make it into a 1 plus TS form. This is very, very important. Then second step, find 20 log K value and draw on the plot. Okay. Then third one, we need to draw a line of appropriate slope. Why I am telling is here, this appropriate slope depends on the number of poles or number of zeros at origin. Okay, that we'll discuss when discussing the problem. Appropriate slope for representing the poles. Representing poles or zeros at origin. This is the thing which you need to do. Next, what we have to do is, after drawing this, line of slope at origin, which is passing through, this is passing through intersection point, that is omega is equal to 1 and 0 dB line. Next is fourth one. We need to shift, that is what we discussed while discussing the key and poles at origin. Shift the intersection point. Onto the 20 log K line. And then draw parallel line, to the line drawn, here. That is the line drawn in step 3. Means whatever the line we have drawn approximate slope, to that line of slope we need to draw a parallel line passing through the intersection point. Passing through the 20 log K line intersection point, because we are shifting this intersection point onto the 20 log K line. That has to be passed through that point. We need to draw parallel to the line drawn in the third step. Next is fifth one. Change the slope of line. Change the slope of the magnitude line or resultant magnitude line. Change the slope. This is very important. We are going to change the slope. Where we are going to change the slope? At corner frequencies. So corner frequencies for each simple pole is different. For each simple zero is different. For each quadratic pole is different. For each quadratic zero is also different. Okay. Corner frequencies. Now continue this till next corner frequency line. Keep going with this corner frequency lines. Okay. Next, sixth one is prepare the phase angle table. This is the simple sixth step. Prepare the phase angle table. What are the factors are there? For each factor, what is the phase angle contribution? That we need to form in the form of table and and obtain obtain omega and phase resultant versus, we can say, versus omega versus phase resultant by calculations. And very importantly, we need to know is at every corner frequency, at at every corner frequency, there should be change in slope. There should be change in slope of magnitude line. Change in slope of magnitude line. Okay, so this is very important. Afterwards, we need to know some of the terms which are used in this Bode plot. So the terms are generally, we can gain crossover frequency, gain crossover frequency, phase crossover frequency, third one is gain margin, fourth one is phase margin. These are the four important terms which we need to know when we start with the Bode plot and analyzing the stability of the system. So we'll discuss one by one. One is gain crossover frequency. Gain crossover frequency. What is this gain crossover frequency? Is nothing but the frequency. It is the frequency at which magnitude of g of j omega and h of j omega is unity, means I can say mod of g of j omega h of j omega is equal to 1 at omega is equal to omega gc, means it is the frequency at which the gain crossover frequency I'll represent as omega gc. So at omega equal to omega gc, the magnitude of this is going to be 1. So if it is 1, if I apply this 20 log k, because this magnitude is 1, if I apply this 20 log mod of g of j omega and h of j omega, which is nothing but 0 dB, it means that it is the 0 dB line where it crosses the magnitude plot crosses the 0 dB line. That point is called as gain crossover frequency. Okay, it is also defined as the frequency at which the magnitude is 0 dB. So both are same. It is mod, and if it is represented in the decibels, it is going to be 0 dB. Next. Crossover frequency. sounds everything. Phase crossover frequency. Phase crossover frequency is defined as it is the frequency at which the phase angle of g of j omega h of j omega is minus 180 degrees, means angle of g of j omega h of j omega is equal to minus 180 degrees at omega is equal to omega pc. So at omega equal to omega gc, magnitude is 1. At omega equal to omega pc, the phase angle is minus 180 degrees. That is called as phase crossover frequency. Now, it is denoted as omega pc, p phase crossover frequency. Next, third one is gain margin. Gain margin. This is represented as GM. Gain margin is represented as GM. So here we in the road locus, what we have done, as the system gain increases, the system stability reduces, and for certain value of k it becomes marginally stable, and for certain values of k it will become unstable also. So gain margin is defined as the margin. It is the margin which is allowable. The margin, the gain means system gain k is having the margin. That is, the margin is nothing but it is the allowable to which, it is the gain which is allowable by which the gain can be increased till the system reaches on the verge of instability. It is defined as it is the margin. It is the margin in what? It is in the gain, that is k. Allowable by which gain can be increased. Gain can be increased till the margin value, till system reaches on the verge of instability, So we are finding this, what is the gain margin of the system, means we are finding at to which value of this margin the system can be increased. That is the gain margin. So here the positive gain margin, suppose positive gain margin, if I have positive gain margin, which means that increase in k is possible, before system becomes unstable. So here, as the system is stable and negative gain margin if you have, k is greater than k marginal, because the k value, if it is negative gain margin is there, that means that it is k is k marginal. When k is k marginal, we can say system is unstable in nature. So my negative gain margin will not be not improve the system stability. So minus negative gain margin is going to be give the k as greater than k marginal. So the system will become unstable. So k we need to be reduced to make the system stable. So hence, if you get a k is gain margin as a negative, try to reduce the k. So that system becomes stable. So gain margin is nothing but it is defined as gain margin is equal to 1 by mod of g of j omega h of j omega at omega is equal to omega pc. So gain margin is calculated at phase crossover frequency. So this can be written as in terms of decibels if I want to represent. In terms of decibels if I want to represent, I can write as 20 minus 20 log mod of g of j omega h of j omega at omega is equal to omega pc. So this is how we can calculate the gain margin. This is how we can calculate the gain margin. Next, phase margin. So phase margin, so in this, similar to this gain margin, we are going to find out the phase margin. Phase margin also. In the phase margin, it is possible to introduce. It is possible to introduce the phase lag in the phase. Lag in the phase means how many degrees is the lag in the phase. Say it starts. Say for example, it is 0. Say 90 degrees. There is a lag in the phase of 90 degrees, right? It starts at 90 degrees means there is a lag. It's at 0, it's not starting, it is having the 0 value, and starting at 90 degrees means there is a phase lag of 90 degrees. So introduce the phase lag in the system. That is negative angles without affecting magnitude plot of, that is negative angles. Negative angles we are going to introduce. Negative angles we are going to introduce, that is minus 90 degrees, minus 90 degrees, like that, without affecting the magnitude plot of j of j omega and h of j omega. So here this amount of additional phase lag, the amount of can be introduced, amount of additional phase lag, additional phase lag can be introduced in this system reaches on the verge of instability. Additional phase lag which is introduced in the system reaches on the verge of instability, on the verge of instability is called as phase margin. So phase margin is defined as the amount of additional phase lag which are going to introduced in the system so that the till system reaches on the verge of instability. It is called as phase margin. So if I have a positive phase margin, it means that negative angle introduction in the system is possible. Means the introduction of negative angle, which is discussing here, introduction of the phase angle in the system, that is negative angle. That negative angle introduction is possible before system become unstable. Before system becomes unstable means we can introduce the negative angles. That is additional phase lag we can introduce. In the system so that the system can become stable. So it is the possibility is there if the positive phase margin is there, and negative phase margin, that is negative PM is there. It means that the present whatever the phase lag or negative phase lag which is should be changed by adding the phase angle. So hence the phase margin is said to be negative and the system is going to be unstable. In this case, system is unstable in this case. So when this negative phase margin and even negative gain margin is also, we can say the system is unstable. positive gain margin and positive phase margin if we got, then the system is stable in nature. So if we got the negative gain margin, negative phase margin, then we can say that present negative phase lag is going to be changed by adding the positive angle. Hence we can, PM can become said to be negative in this system. How it can be expressed in this? PM is, PM can be expressed, PM is equal to angle of G of J omega, H of J omega at omega is equal to omega GC. Phase angle is calculated at gain crossover frequency. Gain margin is calculated at phase crossover frequency. So this is nothing but I can take it as, and of course minus of negative angle need to be introduced, right? So minus 180 degrees. Minus 180 degrees. So this is written as phase margin is equal to 180 degrees plus angle of G of J omega, H of J omega at omega is equal to omega GC. So this is the phase angle calculation. Now, the stability based on this gain margin and phase margin, how we are going to draw? Say for example, if I draw a plots, see I have, this is the 0 dB line, say plus 20, plus 40, plus 60, plus 80, then say minus 20. And this is going to be phase angle plot. I mean, phase angle plot also you can draw in the same picture. So if you look at, this is minus 180 degree line, say minus 180 degree line. And I have a Bode plot which is a magnitude, this is called magnitude, and this is a phase angle plot. So in the magnitude plot, say for example, my magnitude plot is like this, which is, and I have got the phase angle. The phase angle I'm going to get, say for example, like this, and I have a phase angle plot, which is, say for example, after calculating the phase angles by using that phase angle equation, then I got like this. Now you look at, this is the magnitude plot, this is the magnitude plot, and this is the phase angle plot. So we have told that the gain crossover frequency is defined as where the magnitude of magnitude plot is going to be crosses the 0 dB line. That point is called as omega GC, that is gain crossover frequency. So at gain crossover frequency, this is the phase angle. So this is the phase angle, so which we can say this amount is the phase angle, because this amount is the phase angle. When you are calculating the phase angle at omega equal to omega GC, that is called as phase margin. Okay. Similarly, this phase angle the phase angle plot crosses the minus 180 degree line. So this is at the point at which it is crosses the minus 180 degree line. That point is called as, omega PC, means phase crossover frequency. The phase crossover frequency is obtained from the phase angle plot. That phase angle plot where it crosses the minus 180 degree line, that point is called as phase crossover frequency. And if you go upward like this, means that this is called gain margin because this is a magnitude, right? So this part up to this means this part which is called as gain margin, So here, if I want to find out whether this gain margin or phase margin, which is positive or negative, that can be obtained. See here, if the point of intersection, that is below 0 dB line, the gain margin which are obtained, if gain margin is obtained below 0 dB line, below 0 dB line, see this is below 0 dB line, so the gain margin is said to be positive. It is a positive. So here I can say it is a positive gain margin. Similarly, if PM is obtained above the 180-degree line, above 180 degrees, so PM is above 180-degree line, obtained as PVM is, so that is also called as positive phase margin. So it is a positive phase margin, and this is going to be a negative, I mean positive gain margin, positive gain margin. So here, if you look at this diagram, both are positive, both are positive, then we can say the system is stable in nature. The system is stable in nature. When it is stable, if you find out the gain margin and phase margin, both are positive, GM and PM both are positive, both are positive, then we can say the system is stable, or omega GC is less than omega PC, or omega PC is less than greater than omega GC, whatever you can say. So this is the condition. Based on this condition, we can say GM and PM both are positive, both are positive. Okay. Similarly, we can calculate the, I mean, when you say the system is unstable, so similarly, if I plot, after plotting the Bode plot, after plotting the Bode plot, this is 0 dB, say 20, say 40, say 60, and say minus 20, and also we can draw the phase angle here only. So say I have minus 180-degree line like this. And if I have phase angle is like this, and my this one is like this, magnitude plot is like this. So now, as we told that the point of intersection is 0 dB, it is going to be gain crossover frequency. Gain crossover frequency. This is omega GC. Similarly, this point is called as phase crossover frequency, that is omega GC. At phase crossover frequency, if I find the magnitude, that is nothing but we can call it as gain margin. That is what we can call it as gain margin. This one is called as gain margin. So here this is the 0 dB line, this is minus 180 dB line, and we are calculating the phase angle, I mean phase margin is at omega GC. So this is phase margin. If you look at the gain margin in this case, the gain margin in this case, so here I got the gain margin, and here I got the phase margin. As we told in the beginning, if the gain margin is below 0 dB line, then it is called positive. If it is above 0 dB line, then it is called negative gain margin. And similarly, phase margin, if it is above the 180-degree line, then it is called positive phase margin. If it is below the 180-degree line, then it is said to be negative phase margin. If both are negative, that is GM and PM both are negative, then we can say system is unstable. We can say system is unstable in nature. So we can say here omega PC is less than omega GC. In the previous case, omega GC is less than omega PC. In this case, omega PC is less than omega GC. Right. So now one more condition, that is marginally stable. When it is a system is said to be marginally stable is, say for example, the Bode plot is here and say this is the phase angle plot, assuming that it is crosses the phase angle plot like this, and you have got a this is what the point we can call it as omega gc, and okay, so this point is called as omega gc, and here the same point is, if you plot the line, both are on the same value, that is omega gc is equal to omega pc. So if you calculate the gain margin and phase margin for both cases, gm is equal to pm, that is equal to 0. Gain margin is 0 dB. Okay, I'll write like this: gain margin is 0 dB. Gain margin is 0 dB. Phase margin is 0 degrees. In this case, gain margin is 0, phase margin is 0. Okay, so then, and also we can say it is 0 dB line, and say 20, say 40, say 60, whatever it is, a minus 70 degrees line, 0 dB and minus 70 degrees. So here omega gc is equal to omega pc, and gm is equal to 0 and pm is equal to 0. Then system is said to be marginally stable. You can say marginally stable systems. Okay, so we can say the system is marginally stable system. So with this, we'll stop today and at least have an idea about how the system stability can be studied and how to sketch the Bode plot. So I'll stop today. Next class we'll discuss the construction of Bode plot.